In the last lecture, we understood what force can do. We will use that understanding to develop the laws of motion, the first two laws of motion. So we will start with the concept of equilibrium and how force disturbs it. Equilibrium does not mean a state of rest. Equilibrium means the state where there is no net force. So the body may be moving but with a constant velocity. How a force changes that state, and that will take us to Newton's first law. And then we'll develop the concept of momentum, linear momentum, and how force changes that. And that will lead us to develop Newton's second law, and then we'll talk of impulse and examples. But I can tell you this, that Newton's second law is such that it makes people's heads spin. Quite often they are not able to apply this law properly to solve a numerical. Welcome to the portals of what I call the real learning, and therefore don't skip at all and listen carefully right till the end. Let's come to the all important chapter, Newton's laws of motion. There are three laws. In this session, we'll talk of the first two laws. Actually, the first law we have mentioned earlier. This is the first law. Every body continues to be in a state of rest or of uniform motion in a straight line, that is constant velocity, unless acted upon by an external force. No external force, no change in state. Mathematically, we can express it like this. The acceleration of a body is zero if and only if the sum of all the external forces on it is zero. There may be many forces acting. We can always find the net force. If that is zero, then the acceleration is zero. Otherwise, it won't be zero. And the acceleration of the body will be in the direction of the net force. That is called an equilibrium if the net force is zero. And static equilibrium means body at rest. Dynamic equilibrium means body with a constant velocity. Both of them are equivalent states, namely unaccelerated state. So force causes change in velocity or acceleration. Now, there is this concept of inertia which talks about resistance to change. What do we mean by that? A body wants to oppose a change in its state. If it is at rest, wants to be at rest. If it is at constant velocity, wants to maintain the same velocity. Resistance means how much effort we have to apply to change it. Larger the effort, larger the resistance. So greater the mass, greater is the resistance offered by the body for any attempt to change its state. So mass is a measure of inertia. So the first law is also called the law of inertia. But don't take the concept of inertia too far. We'll be talking about an example where this concept of inertia is taken too far, incorrectly. Very important to understand that force causes acceleration. If that force stops, then the acceleration also stops, and it can change instantaneously. Example from NCERT. A small spaceship is accelerating in interstellar space at a constant rate a. An astronaut who was inside accidentally gets separated. What is his acceleration right now? Assume that there are no nearby stars to exert any kind of gravitational force on him. He comes out of the spacecraft. Now there is no force on him. Therefore, no acceleration. The acceleration will change immediately, but the velocity cannot change instantaneously. Acceleration is rate of change of velocity. Assume that there is some change, maybe small, maybe large, but instantly means this is zero. If that is zero, then this goes to infinity, which is not possible. So velocity cannot change instantly, but acceleration can change. Now, the concept of momentum, which will help us to develop the second law. Think of this race. These guys are going with the same velocity, almost the same velocity, but one guy is fatter. Who is more difficult to stop? Think about it. Who is more difficult to stop? Meaning, how much force you have to apply to stop him? Well, the fatter guy is more difficult to stop, so mass has got something to do with it. Second example, Usain Bolt, very fast runner. Take two cases. One when he is running, other when he is walking. When is he more difficult to stop? Same person. When is he more difficult to stop? When he is running. So velocity has got something to do with it. Third case. A building is on fire, a man is caught over there, and the only way he can save is to jump from the second floor. If he jumps this side where there's a concrete floor, he will break his leg. But if he jumps on the other side, he will not. Same man, same speed while hitting the floor. What's the difference? The sand yields, giving more time. The foot will go into the sand, gives more time to stop. More time to stop, less force exerted on his leg, therefore the leg doesn't break. Time has got something to do with it. Putting it all together, force is proportional to mass into velocity upon time. And the mass into velocity term is called momentum. It's a vector written as P, mass into velocity. The direction of the momentum of a body is the same as the direction of the velocity of the body. In order to stop a motion in the case of rotation, we need something called torque or moment of a force. Torque is written as tau, and that's a vector. That is force multiplied by perpendicular distance, not any distance. And what is this perpendicular distance? This force exerted on this bar will be able to stop this wheel, but this force cannot. This force is passing through this point about which it is rotating. Now, the torque is always about a point, and we have to calculate the torque about the point about which it is rotating. This is the line of action of the force. Perpendicular distance is this. So there is a torque which will be like this, which will cause a negative acceleration and then stop it. But this force is passing through it. The distance of the line of action of the force from this point is zero. This guy doesn't exert any torque. So to stop a rotating motion, we need a torque. Also to start a rotating motion, we need a torque. The torque or a couple required to stop a rotating body is directly proportional to not linear momentum now, but angular momentum of the body and inversely proportional to the time. So in linear motion, we say force is proportional to the change in momentum by time. In rotational motion, we say torque is proportional to the rate of change of angular momentum. And what is a couple? Couple is, well, two forces equal and opposite, like this. This will cause this body to rotate anti-clockwise. So that is the concept of torque. Torque requires a force. No questions. Any change in motion requires a force. But it is not just the force, we need the torque, which means force into a certain non-zero perpendicular distance of the line of action of the force from the point about which it is rotating. So second law can be stated like this. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction of the force. The rate of change of momentum of a body is directly proportional to the force. That means this is the rate of change of momentum, and we can say force is proportional to the rate of change of momentum. That is second law. Now momentum is mv, so delta mv. Now m and v, they are two separate quantities, and both can change. Mass can also change, like in a rocket. it is ejecting gases, the mass is reducing. So mass may not be constant. When you want to calculate the change in a product of two quantities and both of them can change, then the principle is the first quantity into the rate of change of the second plus the second into the rate of change of the first. This is second law. In a special case that mass is constant, then delta m is zero. Delta means change, that is zero. Then delta m zero means this term vanishes and we are only left with m delta v by delta t, and delta v by delta t is acceleration, so force equal to ma. Newton's second law of motion is often written as F equal to ma, but strictly that is not correct. The correct expression is F is equal to delta P by delta T. It is actually equal to the constant of proportionality is 1 by choosing appropriate units in SI. F equal to delta P by delta T converts to F equal to ma if the mass is constant, which is the case in 95% of the cases, but generally no. Now, if mass is constant, then we write F equal to ma and it can be applied along x, y, z. The x component of the force is equal to mass into x component of the acceleration, similarly for y and z. And we can see here that you write acceleration as force upon mass. Mass is not merely the quantity of matter. It is that characteristic of the body which decides how much acceleration would be produced in a body under a given force. Larger the mass, smaller the acceleration. Smaller the mass, larger the acceleration for a given force. That is why we say mass is a measure of inertia. Larger the mass, smaller the acceleration. Right? And this is a very, very important law. In fact, this is the most important amongst the three. Mass may not be constant. Take one case. Einstein's special theory of relativity states that the mass changes with speed. If you increase the speed, then the mass changes, mass increases. Therefore, the concept of rest mass versus relativistic mass. Rest mass is when the speed is zero. Relativistic mass when the speed is some quantity v. So, relativistic mass is equal to the rest mass divided by root 1 minus v square by c square. If v is very small compared to c, then v square by c square becomes a very small number compared to 1. We can ignore it, and then mass is equal to mo. No difference between relativistic mass and rest mass. Then mass is constant. So delta P is delta mv, and that is always correct. So delta P is m delta v plus v delta m. That is always correct. But you can't write delta P is equal to only m delta v. You can't write only the first term. The second term you can ignore only if delta m is zero. That means mass is constant. That means speed is very small compared to c. Very important to appreciate this point. F equal to ma is correct only if the speed of the body is very small compared to c. But to put things in perspective, even a very fast moving spacecraft has a speed much, much less than the speed of light. So usually F equal to ma is applicable. Compare mass and velocity here. Let's put it together. When the speed is zero, then the mass is equal to the rest mass. And that continues as you increase the speed up until 10% the speed of light. After that, this quantity in the denominator is not equal to 1, becomes less than 1, and the mass increases. And when the speed becomes equal to c, then v by c is equal to 1, and the denominator goes to 0, mass tends to infinity when the speed equals c. Talking of momentum versus velocity, momentum is equal to mass into velocity. As the velocity increases, the momentum also increases linearly. Mass is constant up until then. After that, mass also increases, and therefore the momentum tends to infinity as the speed tends to the speed of light. So F equal to ma, if you see, rate of change of momentum is this, and delta p is delta mv always. If v is very small compared to c, then delta p by delta t is ma. Now this proportionality thing can be written as equal to, because this k constant is equal to 1 by a suitable choice of units like the SI units. If mass is 1 kg and acceleration is 1 meter per second square, then the force is 1 Newton, and vectorially we write as F equal to ma. The acceleration will always be in the direction of the net force at any instant. At any instant. If the net force changes, then acceleration will also change immediately. Another way, Vi initial velocity, Vf final velocity, initial momentum mvi, final momentum mvf, delta p is final minus initial divided by delta t. If you do, then m taken outside this quantity is final minus initial velocity, means change in velocity upon time. That is acceleration. So F equal to ma. Plotting A versus F, remember A is equal to F by m. If mass is constant, then acceleration is directly proportional to the force applied. But if you keep force constant, then as you increase the mass, the acceleration will reduce, and it is a hyperbolic curve. Consider a rocket. The mass is reducing. Mass is reducing, right? Suppose I take a case, it is rarely so, but let's assume that the velocity is constant. Mass is not constant. Remember, momentum is equal to mass into velocity. I'm assuming velocity is constant, but mass is reducing, so momentum is reducing. Momentum is reducing. Momentum is changing. There must be a force on it. And that force must be negative, opposite to the velocity. Because m is reducing means delta m is negative. Delta P is delta mv always, but that is equal to V delta m in this case because delta V is 0. The second term, that is m delta V, is 0. So it is only V delta m, but delta m is negative because mass is reducing. Change in mass is negative. So this delta P is negative. That means this V delta m, delta P is a negative quantity, and that means the force on the rocket is delta P by delta T. That is also a negative quantity. There is a force in the negative direction, that means opposite to the velocity. As we talked about, the delta V is 0, therefore this term vanishes in this particular case, and it is only V delta M by delta T, which is the same thing as this one. Clear? Another quantity is impulse, which is simply force into time. F equal to delta P by delta T. Therefore, F delta T is delta P. This quantity is impulse, and this quantity is change in momentum. Impulse is also a vector. That means whatever is the direction of the impulse on a body, the change in momentum will be in the same direction. Remember, change in momentum is also a vector. Delta P is also a vector. The units of change in momentum will be the same as momentum, that is kg meter per second, mass into velocity. Impulse will have the same units, kg meter per second. Now, suppose a force is applied for the same time on two different bodies. Same force, same time, hence same impulse. Hence same change in momentum on both the bodies. But the lighter of the two bodies will acquire a greater speed. Why? The change in momentum is the same. Momentum is mass into velocity, right? Vector relationship. So change in momentum will be m delta v. Mass is not changing, so v delta m term is 0. This is the same for both. If the mass is smaller, this will be larger. The change in velocity will be larger. So the lighter body is going to acquire a greater velocity because it has a smaller mass for the same impulse. Look at this ball bouncing up and down. When it hits the ground, it is changing its direction. Momentum is changing. We are saying that it rebounds with the same speed. It rebounds with the same speed, but velocity is reversing. That means momentum is reversing. Initial momentum downward, final momentum upward. Downward is negative, upward is positive. What is the change in momentum? Final minus initial. Final is plus mv, upwards, minus. Initial is minus mv, so this becomes 2mv. That means the change momentum vector is positive and the impulse is along the direction of the change momentum vector. Remember this, very important. Let's take a small question from NCRT. A batsman hits back a ball straight towards the bowler without changing its speed. If the mass of the ball is so much, what is the impulse? We just calculated. If you return with the same speed, then the change in momentum is 2mv. Magnitude is 2mv. Like this. Ball was coming and the batsman put his bat and pushed it straight towards the bowler. The speed reversed. Speed is the same, but the direction reversed. So initial momentum is positive in this direction, plus mv, mv 1.8 kg meter per second. Final momentum is minus mv, minus 1.8 kg meter per second. Delta p is final minus initial minus. This is actually minus 2 mv. Minus means this change in momentum is like this. And the impulse was also like this. Obviously, the force exerted by the batsman was like this. The impulse would be along the same direction, and the change in momentum will also be in the same direction. Now, there's a relationship between kinetic energy and momentum. Kinetic energy is the energy possessed by virtue of its motion, and the expression for kinetic energy is half mv square. Half mv square. What is this v here? It is not velocity. It is speed, because v square is nothing but v dot v, which is a scalar quantity. So we are talking of square of the speed. Hence, it doesn't matter whether the body is going this way or whether the body is going that way. Kinetic energy doesn't care about the direction. It doesn't care about the direction of the velocity. It only cares about the speed. So whether a body is going this way or whether it is going that way, it is not that this way it is positive kinetic energy, this way it is negative kinetic energy. It is always positive. Kinetic energy is never negative. It is always positive, or it may be zero, but never negative. Now, I multiply and divide by m, so it becomes m square v square divided by m. This is mv square, that means p square. And p square also is equal to p dot p. So, kinetic energy is equal to p square by 2m. Now you may wonder, kinetic energy is a scalar quantity, energy is a scalar quantity, momentum is a vector quantity. How can you relate the two? Well, you can, because this is not a vector. P square is a scalar, it is p dot p. Let us do a small question. Suppose a truck and a scooter have the same kinetic energy. Who has got the greater speed and who has got the greater momentum? Let's equate the kinetic energy. Half into the mass of the truck into the speed of the truck square is equal to the kinetic energy of the scooter. Half into mass of scooter into the speed of scooter square, half cancels. Mass of the truck is very much larger than the mass of the scooter. Therefore, the speed of the truck should be very much smaller than the speed of the scooter. Because of this equality, hence the answer is scooter has got a greater speed. Whose momentum is higher? We can see here that for the same Ke, momentum is proportional to Square root of the mass. Whoever has got the greater mass has got the greater momentum. So the answer is truck. Very interesting. Same kinetic energy. Scooter has got the greater speed, but truck has got the greater momentum. All that is fine, but only for a single body. For multiple bodies, never apply this because addition of momentums must be done in a vector manner. Consider this beautiful question. There is a system of two masses. It is given that the magnitude of momentum of the system is zero. Can we conclude that the kinetic energy of the system is also zero? Momentum of the system vector, magnitude means we write like this is equal to zero. That means the vector sum of the two momentums is the momentum of the system. Then we take the magnitude that is given to be zero. The answer is not necessarily. It may be, but not always. Take an example. Two bodies going in opposite directions, P1, P2. These are vectors. They may cancel out if they are equal in magnitude. P1 plus P2 vectorially is zero. But this guy has got a speed, this guy has got a speed. When you add the kinetic energies, both are positive quantities, they won't cancel. So the answer is that it is not necessary that the kinetic energy of the system should be zero. In only one case, it will be zero, that is, both masses are at rest. Momentum of the first body is zero, momentum of the second body is zero, momentum of the system is zero. And the kinetic energy of each mass is also zero because they are at rest. So only in that special case this is true, otherwise not. So be very careful about kinetic energy and momentum relationship in the case of multiple bodies. Do not go and apply this equation. It is only for a single body. Finally, let us do some numericals from NCERT. There's a bullet of this mass moving with this speed enters a heavy wooden block and is stopped after covering a distance of 60 centimeter within the block. What is the average resistive force exerted on the bullet by the block? So the mass is given, the initial speed is given, and the final speed is zero. It comes to rest, and the distance traveled is zero point 0.6 meters, right? So to know the force, we should know the acceleration. Average means we can take the acceleration to be constant. In such a case, we can apply v square is equal to u square plus 2as. V is 0. This is 90 square plus 2. A is whatever we don't know, and S is zero point 0.6. Therefore, A is equal to minus 90 square divided by 2 into zero point 0.6, whatever it is. Minus means it's a retardation, and therefore the force is equal to mass into acceleration. I have dropped the negative sign, implying that this force is negative and it is a resistive force. Second, suppose the motion of a particle of mass m is described by this equation. It is going on the y-axis. What is the force acting on the particle? Mass is given. We want to know the force. For that, we need to know the acceleration, right? Now compare this with s equal to ut plus half at square. Exactly same. That means the acceleration is equal to g. Exactly same. Therefore, the force is equal to mass into acceleration is equal to mg. So those were the two laws of Newton. In the next session, we will talk about the third law of motion.